Okay, so for this one, I'll actually talk about the special thing of wave interference and how it actually, how we can use trig to actually do some very interesting application and see why things are. So, as you may know, there's good things there's things that sound good in music, and then there's things that actually sound bad. For example, if normally there's this thing in music called a fifth or a chord, and I play it, and the chord normally sounds very harmonious and things like that. So if I play something like this, and normally the two notes normally very match closely in the frequencies and seem to go quite nicely together. But there's also other things when the frequency don't really quite match very well, and they create a phenomenon called beats, which actually makes things sound very nasty. So for example, if I play these two notes, so you can actually hear that there's sort of beats going on. It sort of pulsates very fast, and you can sort of hear a much higher frequency in the thing, right? So as I get closer and closer to this note, but not quite on this note, you can hear the number of beats increase. So this one doesn't have that many beats. This one actually has quite a few. This one has more. And this one, you can just hear the beats, and they're very, very obvious in the thing. So, what actually creates this phenomenon of beats, and then what is it, and how does it actually relate, to acoustics and things like that, and how do we actually model it using trig functions? And the thing is, we actually have enough knowledge now to just do a simple analysis of this beat phenomenon. So it's quite simple. We actually have two notes, right? So notes all have a pitch and a frequency. So remember, we already talked about it. Any wave. So there's also cosine waves too, but I never covered that. So let's just deal with sine waves now, because they're actually, they cover everything actually. Because if you must know, actually, if you have cosine of omega t, this is the same thing as sine of omega t plus pi over 2. So sine with a phase shift gives cosine. And we don't really need to look at cosine. Okay, so we know that a wave is going to have some amplitude and some frequency and maybe some phase shift. So for this example, to keep things simple, let's assume that everything has the same amplitude, and we'll just define that to be 1. And then let's assume no phase shift. Okay? So that means we'll have one wave, and this is going to determine the frequency. This omega is going to determine the frequency of the wave. So when we have one note, so actually it's quite complex, because you'll notice that in musical instruments, they normally have this word called the timbre or something, and it normally shows. So here's like a frequency distribution graph, and then it shows that the instrument has many different of these kinds of frequencies. And if you've seen those old boom boxes that sort of have multiple bars, they actually it's actually about a frequency spectrum of the notes. Okay? So a sine wave is actually very simple. It's like a tuning fork. So a tuning fork creates almost a perfect sine wave, and it normally has a very, very sharp line that says, okay, here is 50 hertz, and this thing will only generate notes at 50 hertz. Whereas for a musical instrument, you might get something at 50 hertz. There may be resonance at 100 hertz. Then there may be some other things between, like at 2/3 the distance, 1/2 the distance, and so on. Okay, so let's assume a simple tuning fork model with two notes. So this means that one note is going to have one frequency, omega 1, and then the other note is going to have a different frequency, omega 2. So for simplicity here, let's just assume 10 hertz and 20 hertz or something like that, right? So then this means the first wave is going to be sine of omega 1 times t, and then the second wave is going to be sine of omega 2 times t, right? So now the interference of these waves means we actually add these two waves together and see what we get. And actually there's a sort of a very fundamental philosophical basis, because it's not just, this addition is actually about pairwise addition, right? That means that if we had two graphs, like this one and maybe another sine graph like this, it means that, for this point, I can directly add the two values here and get my third point, which will be somewhere here. And I can directly add these two values here and get the point, and I connect all these points together, and then it gives me a graph. So this principle in general may not be true, but it seems to be true in physics for waves. And this principle of being able to add the waves together when you play two notes simultaneously is called the principle of superposition. So this makes things very simple because it says that in order to add two waves together, we just have to add the values together for each individual time, right? So this means that, okay, let's call this the whole wave function. Actually, W is a bad thing since it looks like omega. So let's use a special, okay, let's use F, right? So F of t is going to be the entire wave, and superposition says, well, F at 0 is just going to be sine of omega 1 times 0, which is sine of 0 or 0, plus sine of omega 2 times 0. And then F of 1 is going to be sine of omega 1 times 1 plus sine of omega 2 times 1, and so on, right? There's no reason why the waves have to do this, but they do work like that, and it's a very beautiful thing, both in physics and mathematics, that allows us to reason about waves. Right? Sort of a implicit perfection that arises from the natural world that allows us to do certain things like this. Okay, but of course this doesn't tell us very much. Sure, we can drop a plus sign between these two things, but that doesn't really help us in graphing it. We still have to apply each individual point. Well, there's good news now. We actually know how to simplify this function. Okay? You may not think we know right off the bat, but we actually do. So now, if you recall, here is the identity for the sine, the sum sine identity, right? If you recall, so it becomes sine of alpha cosine beta plus cosine alpha sine of beta, right? So this is the sine of sum identity. Well, we can similarly say, what is the sine of alpha minus beta? So minus beta is the same thing as just plus a negative beta, right? So then this thing is just equal to, okay, sine of alpha cosine of negative beta plus cosine alpha sine of negative beta. So there's a few nice things. One is cosine of negative beta is just equal to the cosine of beta. Okay, now why is that? Well, if you look on the unit circle, cosine beta is this horizontal distance, right? So if you rotate it clockwise or you rotate it counterclockwise, it's completely symmetric for the x-coordinate, right? Here it's going to decrease, here it's going to decrease. So it's sort of symmetric clockwise or counterclockwise for cosine of beta. So this is why this is true. So that means cosine negative beta is the same thing as cosine beta. Yeah, so think more in detail about this based on the unit circle, and think about why this has to be true. So that means cosine of negative 10 degrees is equal to cosine of 10 degrees, cosine of negative 70 degrees is equal to cosine of 70 degrees. And why is that true? Just use a unit circle and convince yourself. Now the second thing is sine of negative beta is actually equal to negative sine of beta. And of course, again, it works by the unit circle, is that, if we go this way, here the y is positive, and if we go this way, here the y is negative, and it's exactly symmetric, or it's actually anti-symmetric. You just have to put a negative sign in front of everything, and then you do sine. So again, use the unit circle, do the different values, and convince yourself, why this works. And in general mathematics, functions that do this, like f negative x equals f of x, this is called an even function. So that means cosine is an even function. And functions where f of x is negative x equals negative f of x, this is called an odd function. So sine is an odd function and cosine is even. This is just definition of terminology, and I'm just introducing it here just so you know.